Welcome back to Game Theory 101. I'm William Spaniel. Today's topics are continuous types and cut-point equilibria. This is going to be a long one, so get comfortable. Previously, when we've been looking at games of incomplete information, we've only had a finite number of types of players. In a card game, you could be an ace type, a 2 type, a 3 type, 4 type, and so forth. In another form of game, you could be a prisoner's dilemma type, you could have prisoner's dilemma payoffs, or you could have stag hunt payoffs. An alternative way to think about incomplete information is to not have these discrete type spaces, but to look at a continuum of possible types. For example, your cost for a particular action could be anything between some lower bound and some upper bound. Solving these sorts of games requires a different set of tools than the discrete type game. And that should be straightforward. In the discrete type spaces that we've looked at previously, we figured out that you could combine everything into a matrix and then solve that matrix using the standard Nash equilibrium solution to figure out what your Bayesian Nash equilibrium is to the game. If you have a continuous type set, then you can't combine things neatly into a matrix like that, and so you need to do something else. And that's what we're going to be learning about in this lecture. But fair warning, you'll need to know what probability density functions are, PDFs, and cumulative distribution functions, CDFs, are to be able to fully understand what's going on here. That's because continuous type spaces go into the realm of probability theory, and without probability theory, you can't go anywhere with this. So if you don't know what's going on with probability theory, you're not going to be able to fully understand how we're going about solving this sort of thing, and that's unfortunate. You won't be able to fully grasp what's going on in this lecture or in the next lecture, but then after that, we won't be really using this too much more in the future, so you'll be able to go on with this lecture series, even if you can't get through these particular lectures that we're going to be doing now and in the next one. Okay, so that aside, let's get to the game. This is going to be a volunteer's dilemma. Maybe you've seen this before. 2 players simultaneously choose whether to volunteer or not. Volunteering is costly. You have to pay some amount C greater than 0. If at least one player volunteers, then both receive some sort of benefit, which we standardize at value 1. If no one volunteers, then both players receive a value of 0. They don't get that benefit from someone volunteering. The classic example of this is that some individual desperately needs another person to call the police or an ambulance for them, and there are a couple of pedestrians or bystanders just standing there and watching some sort of situation unfold, which requires the police or an ambulance, and they both have to decide whether to spend the time picking up their phone, calling the police, waiting for the police to arrive, giving the report, and what have you. The payoffs work out like this if we actually look at a matrix. So we have 2 strategies for each player: volunteer, not volunteer. If neither one volunteers, no benefit is achieved. If at least one person volunteers, and let's look at a case where one person volunteers and the other person doesn't, that's either the top right or the bottom left. In those cases, the person who volunteers gets that benefit of 1, but pays their cost, whether that's C1 or C2, depends on which player is the one doing the calling. And the person who does not volunteer gets the full benefit and can free ride. They don't have to pay the costs. If both players volunteer, then they both get the benefit, but they're both paying the cost. So that's what the game looks like. But we're not interested in the complete information game right now. That's stuff we've done before. What we want to know is how the incomplete information game works out. So let's add some incomplete information to this, and specifically incomplete information with a continuous type space. Each player's cost is going to be private information to him or her. So if we're in a situation where someone needs to call the police, you don't know how time-consuming it is going to be for me to call the police. Maybe I really need to get to work or something like that, and I'm going to be fired if I don't. So it's very costly for me to call the police, and more costly than you might anticipate. So I know what my true cost is. I know where my priorities are, whether I really have to get to work or not, and you don't. But we do know each other's distribution function. This is going to be a distribution function that is symmetric, and it's going to be independent. We're going to call that distribution function f of c, c being that cost. Where f of 0 equals 0, no one has a cost lower than 0. F of 1 equals 1, that is, the highest cost that anyone could possibly be paying is equal to 1. And the distribution function is continuous and strictly increasing. So if you think as that cost increases, as C grows higher, there's a larger and larger percentage of people who have a realized cost lower than that particular amount. Okay, so how do we solve this game? Remember that a Bayesian Nash equilibrium is one strategy for every type of player, such that no type has a profitable deviation. With a discrete type space game, those strategy spaces weren't all that complicated. We could think about what strategy for one type is doing, and then another type, and then another type, and so forth. And then we just needed to make sure that each of those types of strategies was optimal. With a continuous type space, we're looking at something that's far, far more complicated, remembering that there are actually an infinite number of types out there. For example, look at this number line right here. This is the range of possible cost types that we have, anywhere from 0 to 1. And this is one possibility of type strategies, where everyone in blue, anyone with a cost type associated with that blue line above it, is volunteering, and everyone with a red line is not volunteering. This is a rather complex situation that we have postulated right here, where the lowest cost types are volunteering, then the next lowest cost types are not volunteering, and then after some of them are volunteering, and then some of them aren't, and then some of them are, and then some of them aren't. This is rather complicated, and this is just one type space strategy that we have constructed. You could move those blue lines and red lines around anywhere you want, and you would have to consider that possibility as well for an equilibrium. Fortunately, however, these games actually aren't that complex to solve. The possibilities, the type spaces, the strategy spaces, they're both very complex in this game. But in these sorts of continuous type space games, actually solving for equilibria isn't that complicated. And that's because we can exploit something known as cutpoint equilibria. Equilibria in these games tend to follow a cut point rule. All types below a certain cut point take one action, and all types above that take the opposite action. So in the case of a volunteer's dilemma, everyone with a cost below a particular cut point is going to volunteer, and everyone above is going to not volunteer. Why is it the case that we get these cut point equilibria? Despite the very, very complicated strategy spaces that were out there, why is it that equilibria usually follow this cut point rule? Well, let's think about this in terms of the volunteer's dilemma again. Suppose that a type with a cost C prime volunteered in equilibrium. Would a type with a cost less than that, C less than C prime, also be volunteering? Would they be contributing or would they not be contributing? Well, if the C prime type is volunteering, then by equilibrium conditions, it needs to be the case that his payoff for volunteering is at least as great as his payoff for not volunteering. Otherwise, it wouldn't be optimal for him to volunteer, and so he shouldn't be volunteering at all. But that means that a type with a lower cost has to find volunteering better than not volunteering. It's less costly for him to volunteer than the C prime type, and the C prime type was willing to volunteer. So if you have a cost less than that, if you have a cost less than your friend, and your friend is willing to volunteer, then you should be willing to volunteer at a lower cost. And so that's why we get these cut point equilibria, where everyone below that threshold needs to be contributing or volunteering, and everyone above is not going to be volunteering. Let's look at the payoff matrix to get a better idea of what's going on here. If you volunteer, you're player 1, it doesn't matter what player 2 does, if she volunteers or she doesn't, because you get a fixed payoff of 1 minus your cost to volunteer. Let's put that on a graph. Here on the x-axis, we have a particular type's cost to volunteer, and on the y-axis, we have the utility for doing that. A type with a low cost, say 0, gets a very high payoff for volunteering, whereas a type with a high cost, say next to 1, gets a low value for volunteering. So the utility for any given type for volunteering is going to be decreasing in that type's cost to volunteer. In contrast, if you do not volunteer, your payoff is now a function of what player 2 does, whether she volunteers or she doesn't. If she volunteers, you get a payoff of 1, and if she doesn't volunteer, you get a payoff of 0. And remember that in a cut point equilibrium, both of those things are happening with positive probability. In a cut point equilibrium, player 2 with very low costs is going to be volunteering, and a Player 2 with a very high cost is not going to be volunteering. So in fact, if you don't volunteer, you're going to get a random distribution between 0 and 1. Let's also put this on the graph. So here, this is the red line. This is your utility for not volunteering. And that's going to be a function of what player 2 does, which is in turn a function of the cost that she has drawn. So you get a value of 1 with some probability, which is going to be f of c. I'll explain that in a second. And you'll get a payoff of 0 with the remaining probability. Now, f of c represents the cumulative distribution function for player 2. And this is mapping out what your utility is as the cut point changes. So f of c says for any given c, what is the percentage of types that falls below that amount? So if you have a cut point of c next to 0, there is essentially no chance that player 2 is going to be drawn as one of those types that is below that cut point and is therefore volunteering, which means your payoff for not volunteering is very low because player 2 is almost certainly not going to be volunteering because the probability of drawing a value below that cut point is so low. In contrast, if the cut point is very high, then the probability of drawing a value less than that cut point is correspondingly high. So in expectation, player 2 is very likely to volunteer, which means your utility for not volunteering is relatively high. And of course, if the cut point is falling somewhere in the middle, then you have a middling value for not volunteering. We can do a little bit of mathematical cleanup there, and you'll notice that this is simply equal to f of c. Now, the way I've drawn this line is specifically for a uniform distribution. And when we get to actually solving this game, I'll be doing it more generally. Without assuming a uniform distribution, we'll look at any distribution function whatsoever. If we put both graphs on top of each other, something interesting happens. They intersect at exactly one point, and that point is going to be magical for us. That is our cut point. With a uniform distribution function, then we get this cut point equal to 1/2. If everyone with a cost less than 1/2 volunteers, and everyone with a cost greater than 1/2 doesn't volunteer, then we have found an equilibrium. And that's going to be an equilibrium for the following reason. A type with a cost exactly equal to 1/2 is indifferent between volunteering and not volunteering, by virtue of the fact that that is where those lines intersect. So anyone with a cost less than 1/2 gets a strictly better payoff for volunteering. The blue line is above the red line. And everyone with a cost above 1/2 has a better payoff for not volunteering, which is why the red line is above the blue line. So this is what we're going to ultimately be solving for. But before I get to that, I want to make one brief point about what this is functionally looking like. This is essentially mixing. If we're an observer, we're not someone who's actually in the game playing the game. We don't see any of our types. We're just observing the game being played. Each player is sometimes volunteering and sometimes not volunteering. And that's despite the fact that all types are playing pure strategies in the Bayesian Nash equilibrium. If we go back a slide here, every type with a cost less than 1/2 is always volunteering. That's a pure strategy. Everyone with a cost type above 1/2 is not volunteering. So all of those types also have a pure strategy. Everyone here is playing pure strategies. But if we're an observer to this game, it looks like to us that mixing is occurring. We don't actually see the types being drawn. We only observe the outcome of the game. We're collecting data on that. The players are as if randomizing. The low types are volunteering, the high types are not volunteering, but we don't observe those cost types. So it looks like there's some randomization going on. In a mixed strategy Nash equilibrium, we also get randomization, but it's being caused by something else. It's being caused by players endogenously choosing to randomize. That's playing up with a coin flip and coming up heads, and then choosing to play down if the coin flip goes to tails. So that's a different type of randomization. In contrast, the Bayesian Nash equilibrium, the randomization is caused by the nature's draw. Nature is drawing either a high cost or a low cost type, and that's what's causing us to observe this randomization. So this is actually going to be very important, and that's going to be the subject of the next lecture. We're going to see that, in fact, mixed strategy Nash equilibria very closely approximate Bayesian Nash equilibria. That's a huge revelation, and we'll talk about that in the next lecture. But what I'm going to do now, after the break in this lecture, is go about solving this game, this volunteer's dilemma, rigorously. So you've seen the intuition for what's going on, and after the break, we will fully solve this game. Let's get to solving this, remembering that it doesn't matter if we're looking at a uniform distribution. As long as the distribution meets the requirements that we had previously, it could look like this, it could look like this, it could look like this. Those are two things I just hand drew. Doesn't matter. As long as it meets the requirements before, this method works. So that's why we're solving it very generally, because cut-point equilibria allow us to do that. It's very powerful. So let's get to calculating that cut-point equilibrium. And the way we're going to do this is to look for a cut point on C for which all of the following are true. The type with cost C star is exactly indifferent between volunteering and not volunteering. Types with costs less than C star strictly prefer to volunteer, and types with a cost greater than C star strictly prefer to not volunteer. So types that find volunteering not very costly volunteer, and types that find volunteering costly don't volunteer. Very intuitive. And because we're looking at a symmetric game, we're going to be looking for symmetric strategies here. Nothing on this slide is new. I just wanted to rigorously put down in words what we're going to be doing for the rest of this method to calculate the cut point equilibrium. Now let's go ahead and start by looking for this indifference point. We need to find a value that makes a player indifferent between volunteering and not volunteering. And we know how to write out those utilities. The utility for volunteering is 1 minus C, and I'm going to go ahead and put C star here because we want to find the particular cut point that's going to make this all work out, and that's going to be C star. And the utility for not volunteering, well, that is going to depend on what the other person is doing. If the other person is volunteering with probability P, then we can write out the utility for not volunteering as P times 1 plus 1 minus P times 0. Obviously, we can do some algebraic simplification there, and we also know that we're trying to calculate the indifference point, so we're going to set those two things equal to each other, and that gets us to this line here, 1 minus C star is equal to P. Now we can do some crazy things. Let's imagine that we are calculating this from the perspective of player 1. We can change that value of P into something that's going to be a little bit more useful for us. P can be represented as f of C2. Remember that f is our cumulative distribution function, and player 2 is also playing a cut point equilibrium. All of the low-cost types for her are going to be volunteering, and all of the high-cost types for her are not going to be volunteering. So everyone below a specific threshold volunteers, and we can write that probability of drawing a type that will volunteer using that cumulative distribution function, f of C2, some cost. So if we replace P in that previous equation, we're now with 1 minus C1 star, doing this for player 1, is equal to f of C2. If player 2 is also playing her equilibrium strategy, which obviously she needs to be doing in an equilibrium, we should be thinking about this in terms of player 2's cut point as well. So we have now 1 minus C1 star equal to f of C2 star. So we have a cut point player 1 and a cut point player 2. And we can do one more thing that will make this all work out for us. If we're looking for a symmetric equilibrium, then those costs, those cut points are going to be identical. We can rewrite that as 1 minus C star is equal to f of C star. And that's actually all we need to do to say that we're done with this game. The claim is that there is a unique solution to 1 minus C star equal to f of C star. And the Bayesian Nash equilibrium is going to be for everyone with a cost level below that C star to volunteer, and everyone with a cost greater than that to not volunteer. And that's all there is to it. And that's basically what we're doing here is what we had done previously in this graph. What we had shown before is that 1 minus C is strictly decreasing, and f of C is strictly increasing. You may recall the intermediate value theorem from some of your high school algebra classes. You probably thought you would never ever use it, but here is an application of that. If you have a strictly increasing function and a strictly decreasing function, then they intersect at exactly one place, and where they intersect is where you are indifferent between those two actions, which is, by definition, that cut point type. When we have an explicit CDF, then we can figure out what exactly that cut point is. So in this case, we had the uniform CDF, and we could calculate that the cut point is actually at 1/2. But if you have any sort of distribution function, it's still going to be true that they're only going to intersect in one place. For example, here, this has now shifted that C star over a bit. So we have more people volunteering and fewer people not volunteering. But the idea is still exactly the same. We have everyone below a particular point volunteering and everyone above a particular point not volunteering. And because that type at C star is exactly indifferent between the two, everyone is taking the optimal action. So that's how you calculate cut point equilibria in continuous type spaces. I hope you enjoyed this, and I hope to see you next time where we see a nice connection between mixed strategy Nash equilibrium and Bayesian Nash equilibrium. Take care.